Well, good morning, class. Today we are going to continue lesson unit, whatever the heck it's called, 2.15, talking about semi-log plots. Yesterday what we realized was that if you have exponential data, you can linearize it by taking the natural log or log base, whatever you want, of both sides, right? So if we use a logarithm on both sides of an exponential equation, we end up with a linear equation, which is cool. So we can linearize our data that way. We're going to continue down the same road of thought, only now, what if we just had tables of data and we needed to determine what kind of model we were working with? Okay? So it says consider these tables below, determine if the data is linear, logarithmic, or exponential, explain how you know. And I don't support your answer with tables. I'm not doing that. What I will do is we'll come up with the equation. So we're not going to use the calculators to get the regression. We're going to use our noodles, our brains. We'll have to use a little bit of calculator on the logarithm one, though, because, well, I don't know what the natural log of, say, like 4 is. All right. But other than that, we can get our equations. Okay, so how do we recognize linear? Linear graphs have a constant rate of change. So when you're looking at your first differences, they'll all be equal to each other, linear. How do we recognize exponential? The first differences are proportional, which means you could find a common ratio if you wanted to in the first differences, right? And how then would we recognize logarithmic? Well, I guess a basic answer would be it's not linear and it's not exponential, but also if it was logarithmic, it would have to be increasing but concave down, because log curves are increasing and concave down. So that's how we recognize them. So let's look at this first one. Let's check out our first differences. To get from 5 to 8 looks like plus 3. To get from 8 to 11, plus 3. From 11 to 14, plus 3. Looks to me like the change in y is constant. So constant rate of change on the y's, what's that tell me? Linear. Boom. And what then is the slope of this linear equation? What's the slope? It's 3, but the equation will have a 3x in it. But the slope is 3. And what then would have been the y-intercept? How'd you know it was 2? Oh, okay, you're not wrong, but you worked really too hard. It's because this one also would have been plus 3, right? So if x was 0, this would have been a 2. But you're absolutely right. So instead of adding 3, you could just subtract 3 and get to 2. That gives us a linear model of 3x plus 2. Boom. So easy. So easy. Perfectly linear. Alrighty. Go to the next one. We'll check out our first differences. Plus 6, plus 12, plus 24. What do you recognize about delta y? It's multiplying by 2 every time, which makes them proportional. Delta y is proportional. Literally doubling. It's times 2 each time on delta y. Let's see if we can find our... Oh, so if it's proportional, what does that tell you? What kind of graph is that? Yeah, so it's an exponential model. What is the exponential base? No, the base. 2. Someone said 3. And what would our a sub 0 be? It would be 3. And the reason why is because, you don't know why? Because this would have had to have been plus 3 in order to keep the doubling pattern correct. So this would have been, if x is 0, y is 3 less than 6. And it would have gotten us this 3 here. So we have our model. Y equals 3 times 2 to the x. You know, you could have gone nuts, and you could have just used the fact that this is clearly a geometric sequence. And so you could have used a1 r to the n minus 1. So you could have said 6 times 2 to the x minus 1. Same equation. Same exact equation. That's if you wanted to set it up as a geometric sequence. So far so good, guys? That's not too bad, right? Not so bad. All right. Let's check out our first differences. Here I have plus 1.4, then plus 0.8, then plus 0.6. So what do we recognize about the y values? The second difference is decreasing. Or you could just see that this number is not as big each time. So what we could say is y is increasing at a decreasing rate. So yeah, the second difference is negative. What? Okay. You can see the y's are increasing. However, the rate that they're increasing is slowing down. That tells us that this graph is increasing and concave down. What's happening right now? Why is he giving me a thumbs up? About what? What? These guys are being weird. So is increasing and it's concave down. What does that make it? So it's logarithmic. Great. Finding the model for a logarithm, I mean, it's never going to be perfect, okay? So what we're going to have to do is we're going to have to play a little bit of a brain game, and we're going to come up with as good of a model as we can, okay? Now we could use this as L1 and L2 and do logarithmic regression, Ln regression, we could. Or we could just try to do it by hand and get a model that's pretty darn close. So I want to do it that way because we have no idea what's going to be on the AP exam, right? So here's what we know. We know that we're going to use logarithmic regression. And since we don't have any clue what the base is, we're just going to say it's Ln. Not to mention our calculator would do natural log regression. That's how it does. And we would say, all right, let's check the first coordinate. What is the natural log of 1? What is log base b of 1 always going to be equal to? Log base b of 1 equals 0. Because every number to the 0 power equals 1. So if I plug in x equals 1, this is 0. But I need a 4. And that's why there's a plus 4 there. And now, to try to figure out if this is good enough, go to the next coordinate. Drop in x equals 2. We're trying to figure out if it's just ln of x plus 4. So we grab our calculator, we pretend that we, I don't know, had the ability to do this by hand. And we say, what is the natural log of 2? Let's see if it is 1.4. Because if it is 1.4, we're done, right? Because it would be 1.4 plus 4. It's not 1.4. What that tells us is this plus 4 wasn't the only thing going on. There must be an unknown multiplier on that natural log of x. And we need to find that. Okay. And the way we do that is we plug in the x comma y and we solve for a. We're going to plug in x comma y and solve for a. X is 2, y is 5.4. So we have 5.4 equals a ln of 2 plus 4. You subtract 4 from both sides. And then you divide by the natural log of 2. So by hand, the multiplier is actually 1.4 over the natural log of 2. And that's the multiplier by hand. So your equation then would be y equals 1.4 over the natural log of 2 ln of x plus 4. Now, I don't know what 1.4 natural log of, divided by the natural log of 2 is, but who cares? That is your model by hand. If you want to know what it is, type it on a calculator. That's fine. Okay? But I'd like for you to see something. I'm going to go, and I'm actually going to do the regression on this thing. And I'm going to ask it to do natural log regression. Stat, calc, ln reg, L1, L2, give it to me now, boink. And it is a really, really good regression. You see how many 9s that is? But look at the A value. Oh, it's A value, which is the vertical shift. It doesn't have the vertical shift at exactly 4, does it? So what that tells us is that this is not a perfect logarithmic equation. It's just really close to being logarithmic. That's what we know. So our goal was not figure out which equation's perfect, but which equation would be a good regressional model to use. So the fact that it doesn't say plus 4 tells us that it's not perfect. I mean, look, r isn't 1, so we know it's not perfect. Okay. And our model's pretty darn close to that. They has that b value is 2.01, 2.0145. So let's see if that's 2.0145. Nope. It's close though, right? It's pretty close. So like you said, it's not perfect. And that's okay. And this last one here. We're going to look at our first differences. Always looking at the first differences. I haven't used blue for first differences. Looks like we lost 6.5. Then we lost 3.25. Then we lost 1.625. What do we see in our change in y's? Well, it is the same, but that didn't have to be true. So based on just what you see here, what do we notice about these change in y's? They're divided by 2. They are proportional. So what we see is that our delta y is proportional. And you said it's dividing by 2. It's halving. And since it is proportional, what kind of model? Exponential. Cool. Now we want our equation. What is the r value or the exponential base? 1/2. And what would our a sub 0 have been then? It would have been 26. Because this would have needed to have said minus 13 to go from x equals 0 to x equals 1. So this would have had to have been a 26 by adding 13 back to it. Our model then is y equals 26 times 1/2 to the x. Or y equals 26 times 2 to the negative x. You could get creative like that. Or you could set it up as a geometric sequence. Y equals 13 to the 1/2 x plus or x minus 1, or 2 to the negative x plus 1. It really doesn't matter. There's so many different ways we could do this. Just throwing them all out there. That way you can remember how we can manipulate exponentials. Because you do have that really big Unit 1, Unit 2 test coming up, covering everything we've done so far this year. But what do you think about this so far? It's not bad, right? All right, let's get back to semilog plots. This is raw data. What we're asked to do is take this raw data and we're being asked to plot this on the semilog plot down below. And we need a semilog plot. I mean, look at these y values. They start off as in the single digits and end up at nearly 10,000. So we're going to graph this raw data, meaning it has not had the natural log used on it yet, or log base, whatever we want to use on it. So graph it. Let's see, what's a good color? I think green. I'm going to plot in green. Now we can't do 0, 0.3 because my y-axis begins at 1. But I can do 2, 1.2. 2, 1.2 is like, I don't know, here-ish. 4, almost 6. What's next? 5, about 12.5. Okay, this is 10. That makes this 20. And I know you want to say 15 is halfway between 10 and 20, but it's not. It's not, because this is not a linear scale. This is a logarithmic scale. I mean, I can prove it to you. Look, halfway between 0 and 10 is 5, right? But look how high up the ladder 5 is. You see that? It's much closer to the number 10 than it is to the number 1. So even though we're looking at 12.6, which is about 12.5, we can't go to say 15 and then cut that zone in half. 12.5 is actually like pretty high up. Something like that. Just make the dot fat so it's hard to argue with you. Okay? Then 6, almost 30. 7, 65. So somewhere between 6 and 7, and it's actually closer to 7 than it is to 6, again, because this is logarithmic. But if the dot's fat enough, it's kind of hard to tell. What's after that? 8, 156. All right, this is 100. This is 200. 150 is closer to the 200 than it is to the 100 on a logarithmic scale. So 8, it's like 3/4 of the way up, basically. Right about there. Now we don't have 9, but we do go to 10, 820. So 10, a little bit bigger than 800. So there's 1,000, 900, 800. It's like right here. Again, make that dot fat, and it's hard to argue with you. Skip over 11, go to 12, 43, 52. Oof. There's 2,000, 3,000, 4,000. 43 is roughly halfway between them. Nice fat dot. And lastly, 13 comma nearly 10,000. Because I'm saying fat dot because I can't get an exact graph. That's why. But if you make your dots nice and fat, then it's hard for anybody to say exactly where you put that. Yeah. Anyway, I have a straight edge, so I'm going to attempt to connect my dots with a ruler. I'm going to get through as many of them as I possibly can. It looks like I hit a lot of them right there. That's pretty good. I know you don't have a ruler. It's not a big deal. What does the graph say about our data? Well, the graph is linear on a semi-log plot. No. Graph is linear on a semi-log plot. So f of x is exponential. What a logarithmic with a semi-log plot does is it takes exponential data and makes it linear. Oh yay, I'm being called. There, recording again. Now we're going to use our graph here, this straight line, to approximate f of 3 and f of 9. So let's go to f of 3. It's about right there. F of 3. I don't know. So it's about halfway between 2 and 3, right? You see that? But if you're looking at our, what looks like frets here, what are we really finding halfway between things? No, I mean like, what is really halfway between these two things? Right about here? You see that's about one? You see that's about halfway between those two things? You don't think though? Like just looking, it doesn't look like that was halfway between my two finger marks? Oh, okay. So it's like 3.5-ish. So this is looking like it could be literally 2.35-ish. I don't know, you want to say about 2.4? It's an estimate. 2.4 feel good? Okay. 2.4 feels good. And the next one says, I'll use blue for this one, f of 9. Well, here's 9. Track it all the way up to here. That's almost to the 4. This was 100, 200, 300. It's almost 400. So if you had to guess, it's about 3/4 of the way up. And again, if you come to here and you try to find 3/4 of the way up, if this was half, the next one would be here-ish. Looks like the 6 mark is about 3/4 of the way up. So I would argue that that's roughly around 360, if I had to. 350, 360, something like that. It's an estimate. We're not perfect. Okay? I don't see a whole lot of understanding, like heads nodding type thing going on. That worries me. See a lot of people on phones. Must mean that all this stuff is really easy. That's good. So I can expect super high grades on the next test from everybody. Awesome. Table at right shows the bacteria population in thousands in a culture at time t in hours. Says make a scatter plot of the data. All right, we're going to start there. Go to our calculators, stat, edit. We need to clear our lists if we have anything in there. So remember, highlight the L, hit clear, enter. Boom, they're cleared. So let's get these things typed in. There, got them typed in. It says make a scatter plot of the data. In case you don't remember how to turn your scatter plots on, hit second, y equals, so I'll take your stat plots. Hit enter on plot 1. And if you have off highlighted, scoot it over to on and hit enter. Now we want to make sure that this graph is going to fit on our grid. So go to window and let's pick an appropriately sized window. It doesn't go past 4, so we think like 0 to 5 feel good. And our y values like 0 to, I don't know, I think 400. There. That should give us a really good image of what's happening right now. Anyway, I don't know where I was before I got interrupted. Oh, that's right, I was about to hit graph so I could see the scatter plot. There it is. Ta-da. Oh, look, it's right there. I don't know why this image is here, but whatever. What does the shape of that plot suggest about a model that would fit this data? Yeah, this is exponential data, so we're going to need an exponential model. So we say it's exponential in nature. That doesn't mean it's perfect, but it does look exponential to me. To linearize the data, find x, ln, y, and complete the table at the right. Now we could go through the process of typing all of these in, or we could work smarter, not harder. Stat, edit, come over to L3, go up, highlight it. See where the cursor is? And just say the natural log of L2. L2 is right here. So second L2, close parentheses, and when you hit enter, it will fill out the table for you. Ta-da! Isn't that nice? Another interrupter? There it is. So yeah, let the calculator do the heavy lifting for us. Boom. So that is our L3 now. Yes, so we have L1, L2, and L3. Part C says, find a linear regression for this information. Well, that's just stat, calc, linear regression. But when we go to do the linear regression, we are not going to use L1, L2 because L2 was exponential data. No, you're going to use L1, L3. That will give you linear data. Boink. And I mean, look at that R value. Nearly perfectly linear. So y hat equals, which is the natural log of y, equals 0.979x plus 1.809, rounded to 3 decimals. And just like before, ta-da, is right here. Part D says use the regression model to find a model of the original data set. So rather than asking the calculator to do an exponential model for us, we're going to use the linear model to get the exponential model. What's a good color? Oh, we'll do orange and blue. Go Gators. All right, so we have the natural log of y equals 0.979x plus 1.809. And we're trying to get y by itself. How do I make the natural log go away? Base e. We're going to use exponential base e on both sides of the equation. These cancel each other out. And I'm left with y equals e raised to the 0.979x plus 1.809. 1.809. But this allows us to play a game of exponents. Look, I have addition in my exponents. That means I was actually multiplying numbers that had the same base. E to the 1.809 times e to the 0.979x. And you can type this on a calculator. Let's see what e to the 1.809 is. About 6.104. There it is. And if you were curious, this e to the, and I'm going to write it over here in like parentheses. I'm going to figure out what e to the 0.979 is. 2.662. So there is an exponential model that doesn't use e. So out of curiosity, stat calc exponential regression on L1, L2. It says it's about 6.107 times 2.661 to the x. So pretty darn close, right? Pretty close. I was just curious. I didn't do that in second period, I should say. I wanted to know how good the model was. It's pretty good. Did you see all those R's? It's a good model. It says use the equation that models the original data to predict the number of bacteria present after 12 hours. And you literally just have to drop a 12 into here. So y equals 6.104 e to the 0.979 times 12. And remember, this is in thousands of bacteria. Woo, that's a lot. 772,157. 0.863 thousand bacteria. So that would be 772,157,863 bacteria. It's a lot. It's a lot of bacteria. All right. I should be able to get one more in. Oof. Nah, we'll call it there. That feels like enough. We'll finish the lesson tomorrow. Thanks, nerds.